Diego, California. Today we'll be going over the probability not so basics. So recall that the probability of some simple event A is the number of outcomes in A over the number of possible outcomes. Also recall that 0 has to be less than or equal to probability of A less than or equal to 1, which makes the complement of A, which we touched on a little bit last time. So remember, complement is denoted by the A with the line over it. So probability of the complement of A, or not A, is equal to 1 minus the probability of A. And that's, of course, if there is just the two events. We also talked about how dependent trials, such as trials without replacement, change the successive probabilities, whereas independent trials retain the same probability, no matter what trial you're on. Now, let's also consider disjoint, also called mutually exclusive events. If A represents the event that Shannon is at the San Elijo campus and B represents the event that Shannon is at the Oceanside campus, if Shannon is currently at the San Elijo campus, what is the probability of A? Good. 1 or 100% because I'm there. Cool? How about the probability of B? If I'm at the San Elijo campus, can I be at the Oceanside campus? No. Okay? So that would be 0 or 0%. Maybe this means that if two events, A and B, are disjoint, then if you know that A occurs, then B cannot occur. Suppose we have a random sample of 40 Mira Costa College students. 25% of these students have Twitter accounts, 50% have Snapchat accounts, and 15% have Twitter and Snapchat accounts. So let's take a look at drawing a picture. Okay, so I've put in a couple circles, and let's model what's happening here. So you can either model it with the actual number of students, or you can model it with the probabilities. The intersection of these two groups, so if we call this one the group that have Twitter accounts, and this one the group that have Snapchat accounts, right? Then what's the probability of the intersection? Good. It was 15%. So I'm going to write that as 0.15. Now, I don't want to double count this, okay? So here I'm looking at the fact that 25% have Twitter accounts. Well, I've already accounted for 15%, right? So over in the circle, just randomly, it would be 10% or 0.10. Good so far? Awesome. Now, looking at the Snapchat accounts, we know that 50% have Snapchat accounts. Well, again, we've used 15%, so there's 35% left, or 0.35. Good so far? Now this, if you add these up without double counting, so what I mean is if I add the 0.35 plus a 0.15 plus a 0.10, I get a total of what? Good, I get a total of 60% or 0.6. So adding these up, so I said adding up the 0.35, the 0.15, and the 0.10, we got 0.60. So have I reached 1 yet? No, right? So what does that mean? That means that there's students out there that don't have Twitter or Snapchat accounts, right? And that's what the rest of the box is for. By the way, this is called a Venn diagram, all right? So here we go. Let's take a look. So if I'm thinking about the outside of the box, right? Or not the outside of the box, the outside of the circles, my bad, in the box, what's going to happen? Well, we know that the total model has to add up to 1 or 100%. We know that 60% or 0.6 of it is taken up. And so in the box, that must mean we're going to have 0.40 or 0.4. So I'll just put that out here. Good so far? Don't you just love probability? I do. Okay, so now let's answer these questions. We've got all the information we need. So how many students from the sample have Twitter accounts? Well, we know that 25% have Twitter accounts from the above information. We also know that there are 40 students. So if we multiply 25% times 40, we will get 0.25 times 40, and that in turn is equal to, very good, 10 students have Twitter accounts. Okay, so why don't you guys try the next couple problems? Go ahead and pause the movie and see how you do. Why don't you go ahead and try B, C, and D? Okay, so let's check this out. What do we have going on here? We've got our how many students from the sample do not have either a Twitter or a Snapchat account? Well, we ascertained that 40%, so this is from up here. All right, how many students from the sample have Snapchat accounts? Well, again, we know that 50% of them have Snapchat accounts. So if we take our 50% times the number of students in the sample, that's half of it, right? So do you see that'll just be 20 students? Okay. All right, how many students from the sample do not have either a Twitter or a Snapchat account? Well, remember we figured out up here that 4/10 of the students, or 40% of the students, don't have either Twitter or a Snapchat account. And again, we need to multiply that by the number of students in the sample. And so that would be 16. And that again, we found over here. We're on a roll, everyone. Okay, so how many students from the sample have both Twitter and Snapchat accounts? So what did we find out? Good, the 15%, right? So if we take 15% times 40, you end up getting, isn't that just 0.15 times 40, which is, well, 10% of 40 is 4, and another half of that would be 6 students. Very good. Cool, cool? Awesome. All right. Now, what is the probability that the students have either a Twitter or a Snapchat account? So we have to be a little bit careful here because we don't want to, double count this intersection area, right? So if you're looking at it using a Venn diagram, one way you can look at it is you can say, okay, I'm only going to count that once, right? So here you can have a Twitter or a Snapchat, and with that one, remember we figured that out actually before when we were looking at the how to find the probability that a student didn't have either. So that ends up being, if I add these three like I did up here, that ends up being our 0.6 or 60%. And again, we had gotten that earlier from up here. Okay, what about the probability that a student from the sample does not have either a Twitter or a Snapchat account? Didn't we find that too? Beautiful. We found that one here, didn't we? So that's just going to be 0.4 or 40%. Okay, now if there is more than one event that can occur in a probabilistic model, then the union of the probability of the events is the sum of the probabilities of each of these events minus the probability of all possible event intersections. Furthermore, the overall sum must be equal to 1. So from our situation above, we would have the probability of a student having a Twitter account, which we found was 0.25. Remember, that was given in the problem. Plus the probability of them having a Snapchat account, which was 0.5. And that again was given in the original problem, minus the probability they have both. So remember, in that yellow intersection area, probability that they have both types of accounts was 0.15, plus the probability that they don't have either, which was 0.4. And when you add all these up, what do we get? The first two summed is 0.75 minus 0.15 is 0.6 plus 0.4 is 1. Yay! So this ends up giving us our general addition rule. So the probability of A or B is going to be the probability of A plus the probability of B minus the probability of their intersection. So here we go. What would happen if the events were mutually exclusive? I mean, why didn't I subtract out any intersection of the probability of not having a Twitter or Snapchat account with the other things? Because they don't connect, right? This 0.40 is not ever going to overlap with either of those circles. So the probability of the intersection of that, non-event, if you will, with the other two is 0. So I didn't have to worry about that. So if you have disjoint events, remember that if one happens, the other cannot. All right? So it turns out, if we look at this definition here and we revisit part E of the situation above, which was that OR statement, probability that a randomly selected student would have a Twitter or a Snapchat account, we could also say, oh, okay, this would be probability of Twitter or Snapchat account. That's going to equal to the probability of having a Twitter account plus the probability of having a Snapchat account minus the probability of having both types. And so remember, these were all given in the problem. I'm doing them as decimals. So this one was 0.25. The next one was 0.5. And the intersection was 0.15, which gives us our same result of 0.6. Good so far? Awesome. All right, so now let's take a look at this example. These are always interesting to look at. So here we've got test results and actual disease status of these subjects. So here we've been given this scenario. 1,500 folks got a positive test result and actually have the disease. 500 got a positive test result and do not have the disease. 100 got a negative result but they have the disease, and 1,900 got a negative test result and they don't have the disease. So here we have all these different numbers, but we don't have any totals. So when you see a contingency table like this, what you want is you make total columns and rows, and here this result, this total here, should be the same adding across as it is adding down. So when I add these two down, do you see I get 1,600? When I add the no's down, that means no disease, I get 2,400. That is equal to 4,000 total subjects. And let's make sure it matches. So 1,500 plus 500 is 2,000, and 100 plus 1,900 is 2,000. So we're good to go. We've got our table set, and we checked that we get this same overall the same sum going adding down as we do adding across in those total column and row. Okay, so let's let D denote the event of randomly selecting a subject with the disease, and let Y denote the event that a randomly selected subject from the sample tests positive for the disease. So instead of having all these other letters, we're going to have they either have the disease or they don't have the disease, so D or not D, and they either tested positive or didn't, so yes or not yes. All right. When a test has a false positive, very scary, it means that a subject when a test has a false positive, it means that a subject, sorry, there's a typo, who does not have the disease tests positive for the disease. So that is scary, but it's almost worse, isn't it? Or probably worse to have a false negative, because that means that the subject tests negative for the disease, but actually has the disease. All right? So I always like to do problems like this so you can understand the thinking for these, understand what a false positive rate means or a false negative rate means. Okay, so looking at our table, the probability that a randomly selected subject has the disease. So you're looking at all possible subjects. So what would your denominator have to be? Beautiful. It would have to be 4,000, because those are all the people that are in the study. All right? And so how many people from the study actually have the disease? What do you think? Well, isn't the disease status right here? Right? And so the total number of people who have the disease is 1,600 out of that 4,000. So if we reduce this, what's it going to be? It'll end up being something along the lines of 2/5. And that, of course, is also equal to 40% if you change it around. Good so far? All right, so what is the probability that a person from the study does not have the disease? Well, we're still going to be dealing with that same denominator, right? Of 4,000, because we're looking at everyone in the study. And people that do not have the disease, I'll try a little different color of blue, are these folks here, right? And so we've got 2,400 folks don't have the disease. Now that ends up being, when you reduce it down, I believe we will get 3/5, which has a corresponding percentage of 60%. Okay, so far? All right, so those are some probabilities, that we've had. Not so bad, a lot of information, but not so bad. Now let's also look at the probability that somebody from the study gets a positive test result. So here, positive test result, we would have, that would be a yes, right, on your test result. So there's 2,000 people that got a positive test result out of the, good, 4,000. So 2,000 out of 4,000 got a positive test result. That's equal to 1/2, or as a decimal, that would be, good, 50%. Well, the probability that we got a negative test result, that the test result was not positive, is going to be either the complement, or you can just look at the table and it would be here, this one, and this one. So you would have, again, 2,000, but for a different reason, over the 4,000. Which of course is 1/2, or 50%. Now a false positive, let's think about this. False positive means the test turned out positive, but you're not sick, you don't have the disease. All right, so let's think about this. Given that we don't have the disease, so how many of the subjects don't have the disease? Beautiful, it was the 2,400. So your denominator is going to change because we know that they're not sick with this disease. But we now want to know if they test positive, right? And so out of the people who do not have the disease, how many test positive? Very good, 500. So we end up getting 5/24, which is approximately 20.8%. And we got these numbers from that's the 500, and remember how before we had gotten the 2,400. Okay, so far? Awesome. All right, now let's look at what it would mean to have a true positive. Wouldn't that mean that we would have, the person would have the disease, right? So we're only going to be looking at the people that have the disease, which was beautiful. 1,600 folks have the disease. Now, how many of those who have the disease tested positive? Perfect, 1,500. So that gives us 15/16 exactly, which is approximately 93.8%. Okay, and let me show you where they came from. So find another color here. So the 1,500 came from there, and then that 1,600 was from the earlier part. Remember where we found that 1,600 folks had the disease. Now we'll be going back and forth here. The probability of a false negative. What does that mean? It means that, good, they have the disease, but they tested negative. And so how many people had the disease again? Beautiful, 1,600. Of those 1,600, how many test negative? Awesome. Sorry, the colors are too similar on that one. Try this one. Okay, so far, so that 100 out of 1,600 test negative. And the 1,600 came from this one. Okay? All right, so just a few more questions here. What about a true negative? That would mean that the person, great, does not have the disease. So we decided that 2,400 did not have the disease. And of those 2,400, how many tested negative? Perfect, 1,900. And so here is the $1,900. And then remember the 2,400 was, oops, wrong color. The 2,400 was this highlight. Good so far? Alrighty. Now, what about the probability that a subject tests positive or has the disease? So using that general rule, let's see. That would mean probability that the test was yes, right? Or they have the disease. And remember that that's going to be the probability that they test positive plus the probability that they have the disease minus the probability, because we don't want to double count, that they have test positive and have the disease. So that would be a that true positive reading, right? Oh, I'm sorry, I didn't reduce these. This would be 1/16, which was approximately 0.063. And then this one over here is exactly 19/24 and approximately 0.792. All right, perfect. Okay, so now that we simplified those, my bad, let's go ahead and take a look at these probabilities. We already found them, didn't we? So the probability of a yes plus the probability of that they have the disease minus the probability of a, and remember this was the same as the true positive, So let's look back. Probability they test positive was 1/2. Probability they have the disease was 2/5. So I'll just look at the percentages. So we have 50% plus 40% for the first two percentages. We had gotten, I think, 50% for that, 40% for probability of having the disease. So I'm getting those from Part A, probability of having the disease, Part C, probability of testing positive. Now, let's look at the table for the intersection. So out of our 4,000 subjects, right, the people who have the disease and test positive, there's 1,500 of them. So we would have 1,500 minus 1,500 over 4,000. Okay. So this would end up being, at the end of the day, approximately 0.525, or actually we're in percentages, so we would have 52.5%. Okay? All right, what is the probability that a subject tests negative or does not have the disease? So that would be probability not positive or does not have the disease. That will be probability of not positive plus the probability person does not have the disease minus the probability that they test negative or not positive and they do not have the disease. So again, we had gotten, I believe, 50% for this one. Probability of not having the disease was Part B, so that was 60%. Minus the probability of that intersection. So again, it's going to be over 4,000 like it was for the last problem. And over here, the probability that of not having the disease and testing negative, or not probability, the number of subjects is 1,900 out of the 4,000 gives you the probability. And when you finish computing that, you get approximately, and this gives us approximately 62.5%. Alrighty, guess what? You just worked with a contingency table. Isn't that awesome? You also just figured out some conditional probabilities. Let's look back at parts E through H, and let's also use our super official definition for conditional probability. So this line in between means given. So this is the probability of some event B given that A happened is equal to the probability of their intersection divided by the probability that the event that A event happened. Ooh, giddy. Now we also have a general multiplication rule. So if we use algebra to manipulate that equation, I mean, you started with probability of B given A equals the probability of A and B divided by the probability of A. And if you multiply both sides by the probability of A, then what happens? We get this to divide out, and so that gives us that the probability of A and B is equal to the probability of A times the probability of B given A. All right, so that'll be a useful rule for us. Okay, so now using this conditional rule over here, right, let's calculate these different rates. So the false positive rate basically is saying that, okay, in this wording, we're looking at the probability that if it's a false positive, it means the person doesn't have the disease, right? So it would be a positive test result given that the person does not have the disease, right? So before, what we did is we made our denominator the number of folks in the study who didn't have the disease. But using this formula, what's going to happen? We're going to have the probability that they test positive and they don't have the disease divided by the probability that they don't have the disease. All right, so let's see what we get for this. So the probability of that intersection is going to be, go back here, so the probability that they test positive and they don't have the disease is going to be test result of positive and don't have the disease is 500 out of the 4,000, right? Okay, so that will be in the numerator. So 500 out of 4,000 divided by, well, don't we already have the probability that they don't have the disease? I believe that one was good, 60%. So when I do that computation, be careful with your conversions and all that, I'm going to get approximately 20.8%. Let's look back and see if it matches. So go back to our original E, dun 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 dun, and look, yay, we got it. Okay, so let's go ahead and do F. Probability of a true positive would mean what? The probability that they tested positive given that they have the disease. So that will be the probability that they tested positive and they have the disease divided by the probability they have the disease. I think we got these probabilities earlier. Yeah, do you see over here we got the probability of Y and D, and that was 1,500 over 4,000 divided by the probability of having the disease, and we found that way earlier, and that was 40%. And that's going to give us an approximate result of 93.8%. And again, let's check it. Our True positive. Good, good. 93.8, 93.8. So a false negative would be this conditional probability that they tested not positive, right? Given that they have the disease. The intersection of a negative test result and having the disease divided by the probability of having the disease. So that intersection is going to be over here. So do you see that there's 100 folks who test negative but they have the disease out of 4,000. So I'll write that in here. We have 100 out of our 4,000 divided by, again, probability of having the disease was 40%. So when you do the computation, you will get approximately 6.3%. And going back to the original G, we got 0.063, but that, of course, is 6.3%. And this one over here is 79.2%. Good, good. All right, the probability of a true negative would be the conditional probability that you do not test positive given you do not have the disease, right? So that's going to be equal to the probability of not testing positive and not having the disease over the probability that we don't have the disease. And I think we have a lot of those things. Probability not having the disease was 60%. And then probability of the intersection, we had gotten that up here, I think. Yes, 1,900 over 4,000. And so that ends up giving us approximately 79.2%. And checking it out, it matches what we got up here. Cool, cool? All right, so that is how one can use a contingency table, and we've shown you how to use the table to find these conditional probabilities, as well as just regular probabilities, and we've also shown you how to use the theoretical way, which is using the formula. All right, very good.